Hello everyone. Welcome to week 8 live session of NPTEL's Introduction to Semiconductor Devices course. I'm Om Maheshwari and today we will solve some questions that will help you with your assignments as well as your exams. So mainly in this week, we will be talking about the threshold voltage, the capacitance voltage CV measurements, and some other non-idealities in the MOS capacitor. So let us start with a brief overview of the slides for this week. I hope you all have watch this week's lectures, and if not, please watch the lectures first, as these MOS is the most important topic of this whole course. Okay, so in ideal condition, we were considering phi m equals to phi s, or phi ms is 0. But in the non-ideal case, phi ms is not 0. So what could happen is when your phi ms is not 0, if you will have to apply this phi ms voltage for for bringing the flat band condition, right? So this phi ms will be your flat band voltage VFB. This is the corrected threshold voltage, and this is phi ms is your flat band voltage VFB that you need to apply to brings the bands to flat. So ideally phi m minus phi s is 0, but in most practical cases this is not true. Okay, so generally in uh, NMOS or PMOS, in the older CMOS technologies, we use the P plus polysilicon or N plus polysilicon as the gate material. So instead of metal, your phi m will become chi plus EC minus EF. Chi plus EC minus EF will become phi m if you have N plus poly or P plus poly. So for P plus poly, your EC minus EF is equals to EG, and for N plus poly, EC minus EF equals to 0. So for this case, phi m equals to chi plus EG, and for this case, phi m equals to chi. So in case for interface and fixed oxide traps, what this means, like, this is another non-ideality when your oxide has some non-idealities on the interface, like there are some fixed charges or traps in the oxide. So what it means is, due to these unwanted fixed charges, your threshold voltage shifts. So this shift is given by S minus Qy by Cox, right? So if Qi is positive, then this shift will be, if Qi is positive, your holes will be repelled, electrons will be attracted to the surface. So you will have a depletion even at Vg equals to 0. So your positive charge is reducing your Vt. So now this another term adds to our flat band voltage. So now for flat band condition, you have to apply phi ms minus qi by Cox. This is your new VFB, flat band voltage. Okay, now let's talk about the capacitance voltage curves. So how it is measured is you bias it somewhere, let's say Vg, then you apply a small signal, then you see how the charge is changing here, right? C equals to dq by dV, and your C is Cox in series with C silicon, I would say. So it could be C accumulation, depletion, or inversion, depending on the region of operation or the bias region. So you might have seen this curve many times. So this is a low frequency capacitance voltage curve. And this is a high frequency capacitance voltage curve for N-type MOSFET. So what happens is the majority carrier response time is 1 to 100 picosecond, very fast, which is compared to the applied frequency. Inversion charges are produced by electron hole pair generation in the depletion region. So this process is slow. Electron hole pair generation process is slow. So it does not react to the high frequency signal. It only is, you can only see that this generation in the low frequency signal. That's why in low frequency we get a CV like this. In high frequency we get CV like this. So to interpret the CV characteristics, so this is a CV for a PMOS. So here we are starting from accumulation, depletion, and this is inversion. Again, it's a low frequency CV since it's going back up. So this value where it's saturated, Cox, the oxide capacitance. So why in accumulation and inversion the CV is Cox? Because you can see it from here. 1 by C is 1 by Cox plus 1 by CSI. So in accumulation and in inversion, CSI dq by dV. So this q is proportional to exponentially proportional to Vg, right? So this CSI becomes very large. So this net series capacitance remains to be Cox. So that's why in both accumulation and inversion, we need for both accumulation and inversion, we have this saturating at Cox. Okay, so we'll see this later. Now let's go to the questions. So this is the first question. Please try to attempt this. Okay, so let us see this question. The question is, which of the following are correct in reference to CV measurements? Statement 1. The capacitance of a MOS capacitor in strong inversion is larger when measured at high frequencies than at low frequencies. Statement 2. At low frequencies, there is enough time for generation of carriers in the depletion region and movement of inverter charges to the oxide silicon interface. So statement 1 and 2 are false. Statement 1 is true. Statement 2 is false. Statement 1 is false. Statement 2 is true. 1 and 2 are true. 1 and 2 are true, but not the same explanation. So the answer to this is option C. Statement 1 is false as statement 2 is true. So if you remember the CV curve, this is in low frequency, this is in high frequency, this is the inversion. So the capacitance in strong inversion is larger when measured at low frequency. So statement 1 is false. At low frequency, there is enough time for generation of carriers in the depletion region, movement of inverter charges to the oxide silicon interface. This is true. Right. Let's see the next one then. A MOS capacitor uses a high K dielectric material with relative permittivity equals to 25 as a replacement for traditional silicon dioxide layer. The silicon dioxide layer has a relative permittivity of 3.9 and a thickness of 10 nanometer. Calculate the equivalent oxide thickness if the high K dielectric is used to achieve the same capacitance as the SiO2 layer. Okay, so let us see how to solve this question. So the question says we need to calculate the equivalent oxide thickness to achieve the same capacitance as the SiO2 layer. So that means for same capacitance, epsilon SiO2 by T SiO2 should be equal to epsilon high K by T high K. So you have to find T high K is epsilon high K into T SiO2 upon epsilon SiO2. This is 25 into 10 nanometer upon 3.9. This gives us 64.1 nanometer. So answer is option C, 65 nanometers. Okay, so next question. Given an ideal MOS capacitor with 10 nanometer gate oxide on p-type silicon, calculate the maximum depletion width. in this question, we have to calculate maximum depletion width. So we know that maximum depletion width WD max is 2 epsilon 2 phi f. If psi s equals to 2 phi f, then there is the maximum depletion width on QNA. And phi f is KT by Q ln Na by Ni, which is 0.026 and 10 to power 16 by 10 to power 10, which is 0.359 volts. Substitute it here. We get 3.06 into 10 to power minus 5 centimeter, which is 0.306 micrometers. So answer is option B. Okay, next question. The same description, determine the minimum capacitance in farad per centimeter square. So let's see how this one is solved. We have to find the minimum capacitance. Minimum capacitance in the CV curve is this is the minimum capacitance, right? So if you remember C min, or I would say 1 by C is 1 by C ox plus 1 by C, and this minimum is in depletion. So it will C depletion. So C minimum will be Cox into CD upon Cox plus CD. So if I replace the values epsilon ox by Tox into epsilon Si by WD upon epsilon ox by Tox plus epsilon Si by WD. So if I rearrange this, epsilon ox, epsilon Si upon epsilon ox WD plus epsilon Si Tox. If you see the values, epsilon ox is 3.9 and epsilon Si is 11.8. So epsilon Si is almost equals to 3 times epsilon ox. We replace this here. What we get is epsilon ox into 3 epsilon ox upon epsilon ox WD plus 3 epsilon ox Tox. Cancel epsilon ox. So we get 3 epsilon ox by WD plus 3 Tox. Now we substitute the values 3 into 3.9 to 8.85 into 10 to the power minus 14. WD we calculated in the previous part, which is 0.306 micrometer, which I can write as 3.06 into 10 to the power minus 5 plus 3 into Tox is 10 nanometer, 3 into 10 into 10 to the power minus 7. Okay, so if you solve this, what you get is 3.08 into 10 to the power minus 8 farad per centimeter square. Cement. Closest one is this 3.15 into 10 to the power minus 8 farad per centimeter square. Okay, so let's see the next one now. The high frequency CV plot for an ideal MOS capacitor as shown is shown in figure. So we have to answer these 6 questions based on this figure. Is this a PMOS or an NMOS? So since it's a high frequency CV, in inversion it must be low. It is low here and this is negative VG. That means it must be PMOS. PMOS, which is the flat band condition. The flat band condition is this one, 4. Inversion is 1. Accumulation is 5. Threshold is 2 and depletion is 3. Okay, so let's take the next one then. Please read this question and try to solve it. So this question asks, From the graph, choose the correct option that describes the effect of increasing doping concentration Na on the threshold voltage Vt of the MOS capacitor. So this was explained well in the video lectures, so I hope you have watched them. So what happens when you increase Na is your depletion with WD decreases because WD is 2 epsilon psi s by QNA. So if Na increases, WD will decrease, and if WD will decrease, the depletion capacitance will increase because CD is epsilon Si by WD. So if WD will decrease, CD will increase. Also, if Na is increasing, your threshold voltage Vt will increase. So from this graph, this Na1 must be the highest and Na must be the highest and NC must be the lowest. So Na is greater than NB is greater than NC. This should be the trend. So option A should be correct. Okay, so let's take the next question. Which of the following statements best explains the behavior of capacitance curve as the doping concentration increases? We have just seen this. As doping concentration increases, what happens is this minimum capacitance increases and threshold voltage also increases. So the answer would be the minimum capacitance increases and the curve shifts towards the higher gate voltages. Which is this option. So let's take the next one. Solve this question. Okay, so let's see this. The gate oxide thickness in MOS capacitor is given. We have to find what is the gate oxide thickness. Given is epsilon SiO2 and the area. So this is an NMOS first of all, and this 7 picofarad will be COX, right? COX is 7 picofarad and COX is epsilon ox into area by TOX, which is 7 into 10 to the power minus 12 is 3.5 into 10 to the power minus 13 into 10 to the power minus 4 on TOX. So if you put everything in centimeter units, we'll get TOX in centimeters. So TX will be 3.5 into 10 to the power minus 17 divided by 7 into 10 to the power minus 12. So it will be zero point 0.5 into 10 to the power minus 5, which is 50 into 10 to the power minus 7 centimeter or 50 nanometers. Option A is correct. Next question. If we have two MOS cap with different oxide thickness TOX 50 nanometer and TOX 150 nanometer, so what happens if the oxide thickness is decreased? So how does the VT shifts? So if TOX reduces, VT also reduces. Why? Because if you remember VT is Vox plus psi s in depletion. So this is QD by Cox plus psi s, and this will be QD epsilon ox by Tox plus psi s. So if Tox will reduce, VT will also reduce. So in CV curve, this is one curve, and let's say it is Tox equals to 50 nanometer. Next you have this is Tox equals to 150 nanometer. So if Tox is decreasing, your curve is shifting to the left side, or if VT is reducing. So answer is VT shifts left. Okay, so this is the last question for today. Please try to attempt it, then we will solve it. Okay, so solve this. A MOS capacitor is fabricated on P-type silicon where the metal work function is 4.1 electron volt. Electron affinity in silicon is 4 electron volts, and the energy difference between conduction band minimum and Fermi level is, that is EC minus EF, is zero point 0.9 electron volt, where EC and EF are the conduction band minimum and the Fermi energy levels of silicon respectively. If the measured flat band voltage of this capacitor is minus 1 volts, then the magnitude of the fixed charge in the oxide semiconductor interface in nanocoulombs per centimeter square is what? Okay, so we are given phi m is 4.1 electron volts, chi is 4 electron volt, and EC minus EF is, which is equals to Q phi C, equals to zero point 0.9 electron volts. So we have to find first phi s. Phi s will be chi plus EC minus EF, or chi plus phi C. So which will be 4 plus 0.9, which is 4.9 electron volts. So phi ms will be phi m minus phi s, which is 4.1 minus 4.9, which is 0.8 minus 0.8 electron volts, plus phi ms. Now we know that the flat band voltage VFB. Okay, so let me write it as VT equals to phi ms minus pi QF by Cox plus QD by Cox plus Is. This part is VFB. So VFB, the flat band voltage, is phi ms minus QF by Cox. So flat band voltage is given minus 1 volts is minus 0.8, as we just calculated, minus QF by Cox. So minus 0.2 is minus QF by Cox. So QF we have to find is 0.2 times Cox, which is 0.2 times epsilon ox by Tox, which is zero point 0.2 into 3.9 into 8.854 into 10 to the power minus 14 upon Tox is 10 into 10 to the power minus 7 in centimeters. So if we solve this, we get QF is 6.9 into 10 to the power minus 9 coulomb per centimeter square, which is 6.9 nanocoulomb per centimeter square. This is the required answer. Answer is option A, 6.9 nanocoulomb per centimeter square. Okay, so this is all for this week. If you have any doubts, please feel free to let me know, or you can also, in the middle of the week, if you have any doubts while studying, please feel free to email me here and we can solve them. So thank you everyone for joining. We'll meet again in the next week.